It's an absolute pleasure to introduce the next speaker who I've worked with for a long time. Not only do I count him as a really close colleague, but he's a great personal friend as well. So I'm delighted to introduce Craig Poland, who's going to talk to you about fibres. Thanks, Craig.
Thanks, Roger. I think I'll echo Professor Seaton's comment. There's a lot to cover and not a lot of time to do it. My interest in fibres coincided with when I first started with Roger many years ago, and initially started in terms of looking at the toxicology and the structure-activity relationships in fibres. Really kind of got entrenched looking at the history of fibres, which covers, well, definitely over the last 100 years, but way further back, and the lessons that we can learn from that, taking to our current understanding in terms of the present, but also our understanding of the future and new technological fibres. Hence, title of my talk, Past, Present and Future. So, very simply, obviously, fibres have been part of human exposures since very early days. I mean, if we take it right the way back for something like naturally occurring fibres, for example, asbestos, then you've got examples of people working and using asbestos as early as 4000 BC. Similar with plant and animal fibres, but as with many exposures to particulates more generally, it was with the Industrial Revolution and the 20th century that exposures and uses really kicked off. So as well as obviously these sort of naturally occurring fibres, more and more we have these man-made fibres, insulation walls such as glass fibre, polymer fibres, and more recently different forms of engineered nanomaterials. So carbon nanotubes is the poster child of it, but there's actually a whole spectrum of different types of nanofibre that are being produced and being used in increasingly different ways. And more recently, there's obviously been a lot of interest in microplastics, nanoplastics in the environment. One of the things that's been often found is that the fibres, especially the ones we inhale, we're all surrounded by our own cloud of plastics from our clothes, that they form fibres as well. So there's a different exposure there. So one of the things that I find quite fascinating, because I'm a bit of a geek when it comes to the Inhaled Particles Symposium, is you go back to the very early publications from it. And again, as you can imagine, the focus was very much on asbestos. And then as you move through, then you have the integration of these more man-made fibres, studies on glass fibres, and often the question of, are these the new asbestos, all the way through to the most recent conference series, where you had a really, a much larger showing of nanoparticles. So one thing, research, and indeed the Inhaled Particles Symposium when it comes to fibres, has always been relevant, it's always been important. Now, in terms of showing the kind of importance aspect, I'm going to stretch the past. And when we think of especially occupational exposure to fibres, generally it's asbestos that comes to people's mind. Now, throughout my lifetime, asbestos has always been, skull and crossbones. And sometimes it's hard for us to actually recognize that in its day, it was a wonder material. The reason why asbestos was so widely used was because it was incredibly useful. Its properties were fundamental for a lot of different processes. And what that meant was it was very widely used, but it was also inappropriately used. This example is a Turner and Newall advertisement. So that's Lady Asbestos, under the overseen by the gods of shipbuilding, engineering, construction, electricity, which shows you some of the big areas that it was used, but also consumer uses. This is an example of crystal asbestos. You used to be able to purchase that as asbestos snow to decorate your Christmas tree with. You look at some of the older films, the original Wizard of Oz, for example, or Bing Crosby and White Christmas, and you see the snow falling down. That's crystal asbestos. So the inappropriate use was incredible. Another issue was because its health impact was relatively poorly understood. We saw the public health issues before we really understood the health hazard and the toxicology. Indeed, 100 years after some of the early studies showing that there's a problem with asbestos, we're still trying to grapple with some of the fundamentals, gene changes, the toxicological pathways, that sort of thing. And one of the things we often very much saw was the regulation and eventually the banning of asbestos was very, very slow to sort of catch up with the imminent public health disaster that was there. Now, asbestos, as I say, is generally one of the first materials that comes to mind when people think of fibres, but not all fibres are asbestos. There's a wide gamut of fibres that are used, some of which can cause health problems, some of which don't. But one thing that's always that I find fascinating about asbestos is there's a big lesson there. And without caution, especially to be kind of seduced by a new wonder material, is that the same problems can happen again. I don't think it'll ever be to the same scale. I mean, as I say, the sheer scale of production, use, and exposure to asbestos was just staggering, but you've still got these issues. And one other thing as well is every time there's a new technological development in fibres, and we discuss it a lot in relation to nanomaterials, are they the new asbestos? But that's been pretty much levelled at most technologically developed fibres over the years. It's been asked of glass fibres, silicon carbide whiskers, and so on and so forth. And so without actually addressing that question early on, to identify whether or not there can be a problem, then you've also got this suspicion by association, which can in turn stifle innovation. So again, moving from the past, so the past was to a certain extent the widespread use and exposure to asbestos, and now we move to the present, and that is the impact of that exposure had. So these are from the Global Burden Disease Summary. So their sort of most recent figures is 239,000 deaths in 2019 were attributable to occupational exposure to asbestos. And we can break that down into a range of diseases that are associated with asbestos exposure. And obviously, these diseases are, to a certain extent, very relevant to other fibre exposures. So these figures are from the HSE's most recent figures in terms of their asbestos-related disease statistics. So in terms of lung cancer, you're talking around about 2,500 asbestos-related deaths each year. Now, lung cancer, given the numerous causes of lung cancer, is kind of difficult to actually eke out specifically asbestos as an attributable, well, a causal factor, but the estimates are around about 2,500. Now, fibrosis, so here asbestosis, this actually quite shocked me. In 2019, there was actually 450 mentions of asbestosis on death certificates, of which the cause of death was directly, 291 was attributed to asbestosis. Now, if we compare that to the 1970s, there's about 100 deaths were attributed to asbestosis. And from my kind of perspective, I was always expecting asbestosis to be, a very high exposure disease. And given the kind of the move away from asbestos, the limited exposure, I was expecting that number to be much lower, especially when you consider the number of new cases in 2019. And another thing that I found interesting, which transcends fibres more generally, but when looking through the HSE's figures, one of the things that was pointed out again and again for different endpoints was the fact that the 2020 numbers have obviously been quite considerably impacted by the sort of COVID pandemic, people not seeing doctors, people not working, not being picked up. And again, I think there's going to be quite a wide impact on this sort of data for a number of different exposures for years to come. So mesothelioma is one of the key diseases that are very much associated with asbestos because it's very rare outside asbestos exposure. It's a cancer, obviously, the lining of the lungs, the pleural space. And again, we're talking a remarkable number, 2,669 deaths in 2019. And again, more and more new cases and non-malignant pleural diseases. These are things like pleural plaques, pleural thickening, again, which can cause disability. So from a past exposure that, it was in the 90s that, late 90s that cryphal asbestos was banned, is still a huge problem today. And it's something, obviously, that is imperative that we can always look to prevent these sorts of public health disasters. So why so harmful? And so where I got into fibres was in relation to the toxicology, and specifically my interest in structure-activity relationships. So that's understanding what properties of the exposure can actually lead to disease. And for fibres, due to many, many years of research, both into asbestos, but a whole range of different fibrous materials, the structure-activity relationship has actually is incredibly well developed and is probably one of the most resilient and relevant in particle toxicology. Now, the definition that we often follow, I often attribute it to the WHO, but it goes back much, much further. I think the first use of this sort of definition was around by the Asbestos Research Council, followed, I think, within months by publication from the BOHS in terms of counting rules for asbestos fibres. And it specifies that they need a length greater than 5 microns, a diameter less than 3 microns, and this length to width ratio, which kind of, describes the elongate shape of greater than 3 to 1. One of the things I'm going to do over the next couple of slides is just delve a little bit more into this structure-activity relationship. But ultimately, it comes down to the fact that they need to be thin, so they're less than 3 microns, which helps make sure that they're respirable, they can penetrate the lungs. They need to be long. So this is an example. These are macrophages that normally clear particles from the deep lung, struggling with these long fibers. So that hinders the clearance, but they also need to be biopersistent. So they don't degrade, they don't break up, and don't fragment within the lung. So they persist there, you can get an accumulation of dose. Those three properties put together really dramatically increases the pathogenicity of a fiber. It's not to suggest that something that is short, not long, and non-biopersistent can't be toxic. I'm not suggesting that at all. But in terms of fiber-specific toxicity, those are the properties that we look out for. So starting off with the first one, so diameter. Now, as I mentioned, a respirable fiber is defined by its diameter. By respirable, I mean it can penetrate right down into the deep lungs, where cell-mediated clearance is the mechanism of clearance. Deposition of fibers in the upper airways are cleared by cilia, so it's not dependent on cells, very rapid, and it's not necessarily hindered by the long shape. And as I mentioned, the definition of a respirable fiber has been presented by HSC, WHO, IARC NIOSH. It's generally across the board. And one of the things that's really important is it's also reflected in the counting rules for fibers. Fibers are defined and counted, so exposure is defined based on these physical chemical properties. It's not based on mass, it's based on a count rule of diameter and length, and obviously the aspect ratio. So the reason why definition of 3 micron, is important is because inhalation and lung deposition, and subsequently the clearance from the lung, is determined by the aerodynamic diameter. Okay, so it's not necessarily the physical diameter of a particle; it's its aerodynamic diameter. It's how it behaves in a stream of air. Now, for a fiber, the aerodynamic diameter is based on its physical diameter density, but not its length. That's why you can have a very, very long fiber penetrate very deep into the lungs. And that's based on the fact that it aligns with the airflow, and you end up with a small aerodynamic diameter. So ultimately, it means that thick fibers, so beyond this 3 micron definition, are non-respirable. Now, that's important because if it's non-respirable, you're not getting a deep lung dose. And so you have not got quite the same issue in terms of toxicity. Where you have deposition either in the upper airways where you get clearance very quickly, or ideally can't even penetrate the airways, you're not getting a dose, so you're not getting the toxicity. And this is actually reflected in terms of EU REACH, so within the classification and labeling regulation, certain fibers, and I'm talking things like ceramic fibers and man-made mineral fibers, can actually be exonerated as a carcinogen based on a diameter parameter. So, as it says here in terms of note R, the classification of a carcinogen need not apply to fibers, blah, 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 basically where it's got a diameter greater than 6 microns. So fibers, your aerodynamic diameter is about 2.5 to 3 times its actual diameter. So that, from a particulate perspective, has a very, very large aerodynamic diameter and would be non-respirable. So the next kind of point on this structure-activity relationship was length. Now, early attempts of addressing exposure to fibers, predominantly asbestos, implemented approaches used for silica dust. So there were mass-based metrics. Okay, so they weren't really specific to the properties within a fiber that can influence its toxicity. But in the 1960s, this changed. So the focus shifted to fibers longer than 5 microns, so moving to the longer fiber fraction, and used phase contrast optical microscopy methods. And many of these methods, well, these methods to a large extent exist today. Very relevant, obviously, to mineral fibers, but not relevant to lower diameter fibers, and I'll touch on that a little later. So why? So one of the main reasons in terms of the importance of this 5 micron definition is what's known as the sort of the Stanton hypothesis. This is some of the early work in the sort of late 70s and 80s of Mill Stanton from the National Cancer Institute in the US. And what they found was by looking at a whole range of different types of fiber, so glass fibers, asbestos fibers of all different sort of shapes and sizes. These were implanted into the pleural space of rodents, and they assessed the response, especially in terms of generation of mesothelioma. What they found was that the incidence of mesothelioma correlated with the longer fiber proportions. Specifically, they found that fibers longer than sort of 8 to 9 microns and with a diameter of sort of less than 0.8 microns were much more prevalent at causing mesothelioma. This was later developed and proven in various other studies, and as well as at the kind of the organ level, the importance of length has been shown more recently. This is a study from NIOSH, and what they did here is they took a range of glass fibers. Through grinding and separating, they managed to get different fractions, and they examined the cellular response, specifically the generation of inflammation. And here what they found was a length sort of cutoff of around about sort of 12 microns. So fibers longer than 12 microns were more challenging for the macrophages to take up, but crucially also stimulated more inflammation. Now, what we're talking about here is obviously these sorts of fibers was mainly asbestos and glass fibers. These were glass fibers, but the applicability of this length threshold was also being confirmed in relation to nanomaterials. So what this paper shows, this is a paper in 2012 by Anna Schinwald, using a whole range of different composition nanomaterials, basically injected straight into the pleural space. So we're bypassing the lung here, but looking at the pleural response for mesothelioma. And what they found was irrespective of the composition. So this is silver nanowires, we've got carbon nanotubes, we've got nickel nanowires. There is a very clear threshold for a length-mediated effect. So here, 4 microns was the longest sort of particulate here, and then we've got the 5 micron nanowires, and again, this sort of step change. It's very interesting that using nanotechnology, and the benefit of nanotechnology was you can very accurately make materials to certain properties. It's very difficult to do when you're looking at naturally occurring materials. So this 5 micron definition, enacted in the sort of the 60s and 70s by BIOPERSISTENCE, etc., has actually been demonstrated quite robustly through this and various other areas of research. So the last component of the structure-activity relationship is this biopersistence. And this is quite a key point, because the ability to persist in a biological environment is actually a key attribute of a pathogenic fiber. It's part of the reason why when I go and get my Christmas decorations out of the loft and I'm crawling through glass fibers, that the risk to myself are relatively low, as opposed to crawling through my dad's loft where there's asbestos, cement and things like that I'm not even going to touch on. And part of this is the fact that through understanding these structure-activity relationships, the composition and the role that can play in biopersistence, fibers have been engineered to be more soluble in the lung and so not present so much of a dose. Because it is where you've got a biopersistent fiber, what you've got is a greater residence time in the lung. So you've got a greater opportunity for biointeractions. With repeated exposure, you've got a greater opportunity for dose accumulation. So whilst you might start off with a relatively small dose, because it's not dissolving, because you're continually being exposed, they accumulate in the lung until you hit a threshold effect. But the other thing as well is you've got a greater opportunity for translocation. You've got fibers deposited in the lung and rapidly dissolving. The opportunity for them to move to other regions, so for example, the pleural space, is less. Now, fiber biopersistence, by the way, is dictated by physiological process. So we're talking clearance by, for example, macrophages within the lung, but also physicochemical processes. So they dissolve or they don't. The two together basically will dictate the retention half-time in the lungs. Now, and again, taking this biopersistence aspect is not used as a definition for fibers per se, but it actually is sometimes used in the regulatory concept. Specifically, again, REACH CLP, you've got certain mineral wools with a certain composition can be exonerated as a carcinogen based on evidence of low biopersistence. So that's within note 2 of the regulation. And effectively, it's got a very defined cutoff. In the installation method, half-life of less than 40 days, it's not classified as a carcinogen. One greater than 40 days, is classified as a carcinogen. So that's an action of toxicology into regulation, which is I find quite interesting. One of the issues with that is all the methods used for that, I mean, and at the moment, specifically applied to mineral wools, are in vivo. So there's quite a burden on animal testing just to prove that. So just to finish up, what we've learned over the years in terms of fiber toxicology has taught us much about how to kind of deal with the concerns of newer materials. And so there are a range of different challenges, one of which is specifically those new materials. So we've got attributes like size and diameter, so nanofibers, new generation of nanofibers, new compositions of micron-sized fibers, and how that might influence their properties and toxicity. And as I've mentioned, microplastics. So there's always the need to identify the potential hazards and risks with a new material. And in certain cases, so for example, with nanofibers, there's the need for new analytical methods and potentially to evolve regulation to be agile and robust. One of the issues is new exposure monitoring methods. As I mentioned before, for mineral fibers, it's optical microscopy, and it's just out with the realms of resolution. You can't use that for things like nanofibers. So there's more a move to things like electron microscopy. But ultimately, we need to be able to balance sensitivity with specificity, but with efficiency, to mean that we can actually detect exposures and understand them. Over the years, there's been new parameters suggested for this kind of structure-activity relationship, things like rigidity, defects in structure, crystallinity, as well as composition. There's the question of whether or not the structure-activity relationship, those three components, should evolve, or whether or not further evolution of that actually means that it's no longer generally applicable. It's more specific. And one of the things that I think is really important is new toxicological methods. Typically, the effects of a lot of fibers is chronic in nature. And so a lot of the hazard analysis, especially on the regulatory context, focus on in vivo assessments. And not just through the number of new fibers out there, but just to the ethical components of that. There is a step change required in the move away from these in vivo these in vivo methods to in vitro alternatives. And there's various people in the room, Martin and Vicky, who very much leading the way in this area of in vitro alternatives to in vivo methods. But one of the things we also need is the ability to integrate that into regulation so that it can actually be used. And that's me. Sorry, Roger, you have to keep that.
Amazing stuff. I think maybe you haven't realized it, but you've just had about 40 years of fiber toxicology distilled into those slides, so you can all go home now being experts in fiber toxicology, which is really annoying. If I'd known that when Ken taught me all this stuff over 10 years, it would have been much easier to do it in 15 minutes. Anyway, questions for Craig? Anyone with Peter?
You shortly mentioned carbon nanotubes for details. I was always worried about carbon nanotubes. Is there any new results about those? Is it true that they are used in was just something in the air, nothing. Is there more information?
To be honest, in terms of the possible public health impact of carbon nanotubes, I think I don't think they've quite transitioned into the sort of industrial uses and scales. I think the properties in terms of the biopathogenicity paradigm are, as has been shown, is applicable to carbon nanotubes. It's not necessarily to suggest that shorter ones may be, non-toxic. It'd just be a different sort of paradigm. But in terms of the kind of the widespread use of it, we're just not there yet. I mean, I've certainly heard the same aspect, the questions about integration into things like tires and the road dust that you could get from that. Given the cost of carbon nanotubes, I don't see that happening anytime soon. But also there'd be the understanding of how the released carbon nanotubes, their properties, if they're held within a polymer matrix and they're not a fibrous particle, then you're not going to have the fibrous effect. But I think as Martin, you've worked on the consideration of road dust and things like that through COMEP. That tire dust is an issue, but not from the perspective of carbon nanotubes just yet. Although I will say, in terms of the, while I've focused on the definition of fiber of the sort of 5 micron length, when you actually look at the ISO definition of a nanofiber, it doesn't specify a minimum length. So there's a kind of slight mismatch there in terms of, what is a true fiber, as I would call it, and what might be regarded as a nanofiber.
Thanks. In the interest of time, I'm going to move on, but we can maybe grab Craig at coffee, okay, and have a discussion about that, Craig. I will give you one of these, even though you don't deserve it, but well done.